these two to create 1/4 ln of x minus 1/8 ln of x squared plus 4 plus c, because this is an indefinite integral. Next problem we have is a center of mass problem. Find the center of mass of the semicircle whose center is the origin and the radius is r and the rho is equal to 2. So if you're doing this problem right, the rho should not change your final answer of your semicircles. But there is a lot. This is probably going to be the longest problem that we're going to do. So with that being said, let's just bring up the formulas that we're going to need to know right off the bat. Movement on the y-axis is equal to rho integral from a to b x times f of x dx. Movement on the x-axis is equal to rho integral from a to b 1/2 times f of x squared dx. Now with the center of mass coordinates being x bar and y bar, x bar is equal to my over m, and y bar is equal to mx over m. Now, just to get a little, just to fully do this problem without doing any shortcuts, I'm going to write out the formula for my here. And the formula for movement, I should make that a lowercase m. Formula for movement is equal to rho integral from a to b square root, well, let's not get to that yet, fx dx. So I'll write that down here. So your rows cancel out. So they're actually going to serve no purpose when we do our calculations. For mx, we'll do the same for mx as well. And those rows cancel. So first thing we got to do now is we got to actually draw the semicircle now. So we have radius r, which is a constant even though it's written as a letter. And if you remember from class, the radius is on the x-axis, so it would be r0. And going to quadrant 2 would be negative r0. This value here is 0, comma, there's really no easy way to remember this, but it's the square root of r squared minus x squared for the y value on that point. So now we need to figure out our my at mx before we could proceed any further with the problem. So most tutorials, they'll tell you that that you could just say that the x bar is 0 because the center of mass is on the origin, but I'm going to actually prove this a little bit more rigorously. So x bar is equal to integral. So our bounds are the radii. So we're going to go from negative r to r. X and then f of x is, so in the formula it's f of x. Y is equal to f of x. And our y for the semicircle is r squared minus x squared dx. Again, the simplest way here is to not do a trigonomic substitution because we have this dangling x there. So we might as well do a u substitution. R squared minus x squared. Du becomes, r is a constant, so it just goes away. Then you have 2x dx. Divide, or should I say u squared is equal to r squared minus x squared. So then you have 2 du, and if you divide both sides by 2, you get du is equal to x dx. So when you plug this back in, you got to convert the r's as well based on what you put as your substituted u. So this becomes actually, we don't have to worry about that at the moment, because we could proceed with the problem as normal without doing that. X bar is equal to, well, this is technically all my. We're just calculating the first part of the x bar. So this becomes integral from negative r to r du. And then this center part becomes square root of u squared, which is just u. I should have put 2u du here. So then you multiply this by u, which gives you u squared. And since we also so we don't have a 2 here where rho would be because we canceled that out earlier, but you're going to see that it's not going to make a difference. So this is equal to u to the third over 3 with limits negative r and r, which will just equal r to the third over 3 minus r to the third over 3, which is just 0. So I'm also going to calculate the movement itself just because we're going to need it for the y bar. But movement is equal to limit from negative r to r squared minus x squared dx. Now that you're not dealing with a pesky x, you could just do a trig sub of r squared minus x squared is equal to with x is equal to r sine theta. Dx is equal to r cosine theta. D theta. Now we got to convert the limits with r and negative r. R is equal to r sine theta. Why? R is an x coordinate. So we gotta treat it like it's an x. We gotta replace x with r. Divide both sides by r, you get 1 sine theta. The theta, sine equals 1 when theta is equal to pi over 2. Negative r is equal to r sine theta. This is the lower bound. Upper bound, lower bound. Negative 1 is equal to 1 sine theta. Theta. So sine becomes negative 1 when theta is equal to negative pi over 2. And now we got the upper and lower bounds to solve for our movement. Movement is equal to negative pi over 2. Pi over 2. um, r squared minus r squared sine squared theta times what we replace the dx with is r cosine theta d theta. So then this turns into you could take out an r here, factor out an r, the square and the root cancel for r, so you could take out r from the square root, and then you could take it outside of the integral because it's a constant. 1 minus sine squared theta is a trigonometric identity of cosine squared theta. They square and the root cancel out, so you just get cosine theta. Okay. Put this r back in because it's just going to be easier that way. So then you can actually combine these two like terms to get you r squared cosine squared theta d theta. Take the r out of the integral and do a power reduction formula on the cosine squared theta. Which would turn into 1 plus cosine 2 theta over 2 d theta. Take the 1/2 out of the radical, out of the integral, which would get you r squared over 2. Actually, that's preemptive. That's too early to do that. Because this has a chance of turning into a variable. We don't want that to happen. We don't want to make any mistakes too soon. We want to keep the 1 plus there, but we could get that 2 out. That's in the denominator. So then this turns into r squared over 2 times this one integral 1 dx d theta just turns into theta pi over 2 negative pi over 2. plus the integral of cosine 2 theta is sine 2 theta. Okay, so with pi over 2 and negative pi over 2. Sorry if that's a little hard to read. R squared over 2. First half is pi over 2 plus pi over 2, which is just pi. But for the second half, you have sine pi minus sine negative pi, which when you put that in a calculator, which I have handy here, that is set to radians. Sine pi is equal to 0. Sine negative pi is also equal to 0. So you have 0 minus 0, which is equal to just 0. So then you're left with pi r squared over 2, which is actually just the semicircle formula. And that's our movement. So basically, going back to x bar for the x coordinate of the centroid, of the center of mass, it would just be, so x bar would just be 0 times 2 over pi r squared, which is just still 0. So now going back to, now we know our x definitively. X bar, y bar. X bar is 0. Now we need to figure out our y bar, which is mx over m. We know our m, so we'll write the first half of that down. Now we need to figure out the rest. Mx is equal to 1/2 integral AB, which at this point we know is negative RR. Which we also know is negative RR. Fx squared dx. This becomes And again, we're not including rho because we canceled it out. 1/2 negative r square root of r squared minus x squared dx. So the square and the radical cancel out, leaving you with just r squared minus x squared. Second thing you would need to do here is, since these are both even functions because they have even exponents, this would be the same as having 2 times the integral from 0 to r. So just going to do that real quick. And then these 2's cancel out. And we don't have rho here again, but we canceled it out already. Now r is a constant, so you're going to end up with r squared x when you integrate it. And then the x is going to turn into x to the third over 3, going from 0 to r. This turns into r to the third minus r to the third over 3 minus 0 times r to the squared, which is just 0, minus x to the third over 3, 0 to the third over 3, which is just 0, so don't include any of that. So this is equal to 2/3 r to the third. And that's the part that we need here. So we'll put r to the third here, and then we'll multiply, we'll invert the fraction so that we could divide it. Actually, no, just leave it as is because it goes on the numerator. Times 2 times 3, which ends up giving us 4r to the third over 3 pi r squared. And because we never have to deal with rho, that as long as you're dealing with a centroid who's rotated about the y-axis on the origin, you'll never have another value besides this for your y bar or the y coordinate of the center of mass. And we'll be going now to number 8 out of 11. So we've got 3 more to go, but these are going to be really quick. I'm probably going to want to get this